Imagine a universe filled with hidden mass that remains elusive to our understanding. Two innovative theories are emerging, offering scientists fresh perspectives on the origins of this mysterious dark matter, and how we might eventually uncover it. One of these theories introduces the concept of a mirror world, a concealed counterpart to the ordinary particles we know, while the other suggests that the early universe's edge acted like a hot surface capable of generating particles, akin to the behavior of a black hole's event horizon. Together, these ideas not only enrich our comprehension of dark matter's beginnings, but also provide testable predictions that align with established physics, steering dark matter research into exciting new avenues. The evolution of the dark matter puzzle. For decades, evidence supporting the existence of invisible matter has been accumulating. Observations show that galaxies rotate at speeds that defy explanation. Clusters of galaxies bend light more than anticipated, and patterns observed in the early universe only make sense if a significant portion of matter is dark. Current estimates suggest that nearly 85% of all matter in the universe is dark, characterized by its cold and slow-moving nature on cosmic scales. Despite numerous ingenious attempts to detect dark matter, the leading candidates have consistently eluded discovery. This ongoing series of negative results has prompted theorists to venture into uncharted territory. Physicist Stefano Profumo from the University of California, Santa Cruz, encapsulates this sentiment. Both mechanisms are highly speculative, but they offer self-contained and calculable scenarios that don't rely on conventional particle dark matter models, which are increasingly under pressure from null experimental results. Exploring new theoretical pathways for dark matter origins. The first theory, recently published in the journal Archive, envisions a mirror sector, a duplicate realm of known particles and forces that interacts only weakly with our own universe. In this hidden dimension, a variant of the strong force could bind what are termed dark quarks into heavy structures known as dark baryons. In the early stages of cosmic history, these could have collapsed into tiny, stable remnants reminiscent of miniature black holes. If produced in sufficient quantities, these dark baryons could account for the universe's missing mass, while remaining undetectable by current instruments. The beauty of this theory lies in its reliance on familiar physics, merely applied to a concealed version of our universe. The second theory, published in the journal Physical Review D, posits that the expanding horizon of the early universe functioned as a particle factory. Following the period of inflation, the cosmos may have experienced a brief phase of accelerated expansion. During this time, the cosmic horizon would have possessed a temperature capable of radiating particles, similar to the behavior of a black hole. If stable particles were indeed produced in this manner, they could constitute dark matter across a vast spectrum of possible masses, ranging from thousands of electron volts to near the Planck scale. Chapter 1. The contributions and challenges of the mirror world. While mirror world models have been proposed for years, a recent study has refined the observed ratio of dark matter to normal matter. This theory employs a mechanism known as the Affleck-Dine process to create an imbalance in both sectors, resulting in a surplus of matter over antimatter. This approach circumvents the need to rely solely on matter-antimatter annihilation. The model presents two primary scenarios. In one, mirror electrons, with masses in the billions of electron volts, serve as the dark matter. In the alternative scenario, dark matter consists of mirror baryons. In both cases, the theory anticipates the existence of a mirror photon with a mass in the million electron-volt range. This photon could elucidate the smoothness observed in small galaxies without conflicting with the formation of larger structures. Additionally, the model predicts a slight but detectable increase in early universe radiation, something that future cosmic background surveys could identify. The horizon production theory, a simpler approach. Profumo's second proposal is more straightforward in its framework. Picture the universe just after the inflationary period, during a phase of nearly steady expansion. In this state, the cosmic horizon behaves like a hot surface, generating particles through quantum effects. If these particles are stable and interact solely via gravity, they could persist as dark matter in the present day. The ultimate quantity of dark matter produced would depend solely on the conditions during this phase and the temperature at which normal expansion commenced. By analyzing specific features of the early universe, scientists could quickly narrow down the potential mass of this type of dark matter. Aligning with established knowledge, both theories favor dark matter that interacts very weakly, which aligns with years of experimental findings that have failed to uncover any signs of strongly interacting particles. Observations of cosmic structures also support the notion of dark matter being cold or only slightly warm, a characteristic that both theories can accommodate. Testing the theories. The mirror world hypothesis can be evaluated through several methods. Small galaxies. Self-interacting dark matter alters the centers of dwarf galaxies, which could be revealed through more detailed stellar mapping. Early radiation. Any additional radiation from the mirror world would leave a detectable imprint in the cosmic microwave background. Mirror photon effects. A mirror photon at the MeV scale would influence structure formation and could be identified indirectly. The horizon production theory could be tested by searching for primordial signals. Gravitational waves or slight deviations in early expansion could indicate a brief accelerated phase. Mass limits. Understanding the temperature at the end of this phase would help constrain the possible mass range for dark matter. Both proposals are part of a broader movement towards exploring dark sector and gravitational production models. Workshops and new research are already delving into similar concepts, from dark photons to particle creation linked to inflation. This shift reflects a growing interest in not just identifying the particle itself, but also understanding the processes that led to its formation. The significance of these theories. These emerging theories regarding the origins of dark matter present a promising new direction. Rather than solely pursuing particles in laboratory settings, they open avenues for discovering clues about dark matter in galaxy surveys, cosmic background maps, and gravitational wave detectors. For science communication, they keep the narrative dynamic, demonstrating that the field evolves even when previous theories fall silent. Recognizing the limitations. Every ambitious theory has its constraints. Mirror sectors could potentially generate excessive radiation or disrupt galaxy formation unless their parameters are finely tuned. The horizon theory must fit within a very brief time frame without contradicting the standard Big Bang model. Both research teams have delineated the conditions necessary for their models to be viable, providing observers with clear targets for investigation. Future directions in the search for dark matter. The next steps involve mapping small galaxies with greater precision, enhancing lensing studies of low-mass halos, measuring early universe radiation with new background surveys, and seeking evidence of short-lived accelerated expansion following inflation. While these paths may not yield a singular answer, they will help to either confirm or refute various theories with greater accuracy. In summary, the exploration of dark matter origins is venturing beyond traditional concepts of thermal freeze-out, entering new realms where gravity, cosmic horizons, and shadowy counterparts of known physics illuminate the way forward. Although these ideas may seem unconventional, they provide scientists with concrete predictions to test in the years to come.